In this video, we're going to be taking some notes on sequences. First off, let's start with the definition. A sequence is just an ordered list that follows a set pattern. In Algebra 2, we're going to talk about two types of sequences, arithmetic sequences and geometric sequences. So, an arithmetic sequence is a sequence with a constant common difference, or in plainer language, where you just have to add a certain number to get from term to term. Here's our first example. If we have 2, 4, 6, 8, 10, what are we doing every time? Every time we add 2 to get to the next term. This number that we add is the common difference, is its name. We call it D for difference. In the second example, we are subtracting 6 each time. So our common difference would be a negative number, because the amount of the common difference is what we add every time to get the next term, and our common difference would be negative 6. In a geometric sequence, a geometric sequence is a sequence with a constant multiplier or a common ratio. So in a geometric, to get from one term to another, you have to multiply by a certain number. Here's our first example. 1, 2, 4, 8, 16, 32, 64. Every time, what did I do to get to the next term? Every time I multiplied by 2 or doubled the previous term. So my common ratio, or the thing that I multiplied by, is 2. We call R the common ratio. In our next example, our numbers are getting smaller. They're becoming fractions. Sometimes with fractions, I think it's easier to look from one fraction to the next to say, what did I multiply by? So if I were looking at these two, to get from 4/9 to 4/27, what do I multiply by? The top stayed the same, so it's 1. The bottom was tripled. And then just go back and look. 12 times 1/3 is 4. 4 times 1/3 is 4/3. So this is our pattern, and our common ratio, or what we multiply by, is 1/3. On the bottom part of the page here, we're supposed to tell whether the sequence is arithmetic or geometric, and then get the common difference or the common ratio, and list the next 3 terms. I'm going to go ahead and do 1 and 2 with you, and we can pick up 3 and 4 later. So as we're looking at our pattern, I want to say, am I adding a number every time or multiplying by a number every time? In this one, I add 5 every time. That makes it arithmetic with a common difference of 5. If I followed this pattern, picking up after 20, if I add 5 to that, my next term would be 25, then 30, then 35. In number 2, what am I doing every time? I'm multiplying by the same number every time, so I'm geometric, and what I'm multiplying by is 1/2, so my common ratio, or R, would equal 1/2. If I follow the pattern, after 1/8, an eighth times a half is a 16th, times a half is 1/32, times a half is 1/64. We're going to leave some blank in this video, and then we'll come back and pick those up in class, or you can try them on your own if you want to. All right, turning the page, we have a new type of definition. Missing terms in an arithmetic sequence are called arithmetic means. We should know that the mean is like the average, right? We know that word, mean means average. So we're looking for what comes in between. If they're arithmetic means, they have to find an arithmetic pattern. So if we started with this example to find the arithmetic mean of 13 and 19, that means put a number in between so that I follow the pattern where if I add a common difference, I would wind up with 19. So for this one, I would have 13 plus 2 differences has to get up to 19. So 2 differences, if I move the 13 over, would be equal to 6. So 1 difference would be equal to 3. That means I add 3 each time to get the next term. So 13 plus 3 is 16, and then if I follow my pattern along, 16 plus 3 should equal 19, which it does. So that means the arithmetic mean of 13 and 19 is equal to 16. We can find more than one arithmetic mean. So you could use the same process. If it said find 3 arithmetic means, that just means that in between the 2 and the negative 22, I'm going to have 3 terms in my sequence. So see if you can do the same type of math that we did above while you pause the video and find 3 arithmetic means of 2 and negative 22. So for this one, I would have added the common difference 4 times to complete the pattern. So I wrote the equation of 2 plus 4d is equal to negative 22. To solve that equation, I would subtract 2 from both sides and then divide both sides to get my common difference is equal to negative 6. So if I then came up to my pattern and said if I start with 2 and I take away 6, I'm at negative 4, and I continued to take away 6 each time to complete the pattern, and then I double checked in the end, does it work? Does negative 16 minus 6 equal negative 22? Yes, it does. So I know my 3 arithmetic means are negative 4, negative 10, and negative 16. We're going to leave the other ones for right now, and you can come back to them later in class. If we scroll down to geometric means, the missing terms in a geometric sequence are called geometric means. So we have the same type of thing going on. To find the geometric mean of 4 and 36, that means if I take 4 and multiply it times my common ratio, I'll get the mean, and then I multiply it times the common ratio again to get 36. So 4 times r has to equal 36. We'd normally write that as 4r squared equals 36. I'd divide both sides by 4 to get r squared is 9, and then I'd square root both sides to get r is 3. So if I go back and plug 3 into my formula, 4 times 3 would give me 12. And then if I do that again, 12 times 3 is 36. So the answer, the geometric mean of 4 and 36 is 12. By the way, this could be plus or minus 3. So technically both 12 and negative 12 could be the geometric mean, but I'm not going to worry about that too much. I'm just going to, if I get 1, I'll be fine with that. All right, so let's try number 8. Find 3 geometric means of 2 and 162. This means I need 3 numbers to come in between 2 and 162, and it has to be geometric, which means I'm going to multiply by r each time. Pause the video while you give that one a try. Okay, so I had 2 times r to the 4th, because there were 4 r's, had to equal 162. I divided both sides by 2 and took the 4th root of 81, because in this equation here I needed to get rid of the 4th power. So the 4th root of 81 was equal to 3. Again, it could have been plus or minus. We're not going to worry about it. So my 3 geometric means are 6, 18, and 54. So you could try 9 and 10 on your own if you wanted to, or we can work on them some more in class. All right, let's turn the page and look at formulas. All right, we have 2 types of formulas we're going to work with in Algebra 2, recursive formulas and explicit formulas. And this is the Latin plural of formulas. All right, so we're going to have some notation that comes up here. First thing to realize is the nth term of a sequence is written as a sub n. That's a with a little subscript or down low and small n, a sub n. So if I were saying a sub 1, that would be the first term I'm talking about. If I wanted a sub 2, that would be the second term. So n tells me which term I'm talking about. All right. A recursive formula is where we're going to start. A recursive formula for a sequence is a rule that defines a new term based on previous terms. So this is the way we usually think. What do I do to the one before it to get the next one? Here's an example. To get the nth term of the sequence 2, 5, 8, 11, we can use the rule, and let me read this to you. A sub n equals a sub n minus 1 plus 3. So a sub n, that was the nth term. A sub n minus 1 would be the term that was 1 less than the one before it, so that's the term before it. So if you're looking for the 5th term, the term before it is the 4th term. And then the plus 3 tells me what I do every time to get the next one. Okay, so let's put this into practice. There are some formulas on the formula sheet for Algebra 2, and it tells you the recursive formula for an arithmetic sequence is this one right here. That is a general form. So a sub n is the nth term. to get the nth term, that equals a sub n minus 1. A sub n minus 1 is the previous term. And d, just like before, d is the common difference. So for any arithmetic sequence, it's going to follow this rule, and this formula will be given to you on a formula sheet. Now, we have to watch out with the recursive formula, because if I'm just telling you add the same number every time, you won't know where to start. So in our example we have right here, they give two pieces to the formula. The first piece is that a sub 1 equals 12. So if I were going to write out this formula, I'd start out with 12 as my first term. That's real important because I need to know how to get the next term. Down here this says the nth term, or the next term, is the term before that minus 6. So it tells me to take 6 away from 12, which gives me 6, which is my second term. Then I'd take 6 away from that to get 0, 6 away from that to get negative 6. So every time in the formula, I'm using the previous answer and I'm subtracting 6 from it. This little bit on the end where it said for n greater than or equal to 2, that just meant for a sub 2, a sub 3, a sub 4, etc. So not for the first one, not where n was equal to 1. I don't care if you write that when you're writing your own formulas, but we've seen that written on the SOL, so we want to point it out to you. Okay, so that's an arithmetic sequence with an explicit or a recursive formula. If we want a recursive formula for a geometric sequence, the difference would be that every time to get the next term, we're going to multiply by the common ratio rather than add the common difference. So the only difference between these two formulas is whether you're adding a number or multiplying by a number. So here's our example. Again, we started out with a sub 1 equals 12, tells us the first term of the sequence is 12. Then in the next line of the formula, it says to get the next term, or the nth term, you're going to take 1/3 times the previous term. So if I start out, if I wanted to find the second term, that's going to be 1/3 times the first term. Well, what was the first term? The first term was 12. So 1/3 of 12 is 4. And now I know that 4 is the next item in my pattern. So if I wanted to find the third term would be 1/3 of the term before it, which was a 4. 1/3 of 4 is 4/3, and that's the next item that goes into my sequence. So then I'm going to do 4/3 times 1/3 equals 4/9, and that's the next thing in the sequence. So every time, what am I doing? I'm multiplying by 1/3. So these were recursive formulas. Again, the thing that makes a recursive formula sort of pop out to you is this a sub n minus 1. All recursive formulas are going to have an a sub n minus 1 in them. The next type of formula that we'll deal with, if we look down the page, is an explicit formula. If you look at all the explicit formula examples, you'll never see that a sub n minus 1 written again. In an explicit formula for a sequence, it's like a function rule, where you plug in any number n to get the nth term. So for example, to get the nth term of the sequence 2, 5, 8, 11, we can use the rule a sub n equals 2 plus the quantity n minus 1. And then I'm going to multiply that by 3 because the common difference between the terms was 3, which is like a slope of a line, and the sequence starts. So next we have the explicit formula for an arithmetic sequence. And here is the formula. I mentioned that these were on the formula sheet, so I'm just going to pull that up real quick. This is our Algebra 2 formula sheet. And if you scroll down on the formula sheet, down here at the bottom, it has sequence and series formulas. Let's see if it's going to keep moving for us. And you can see the formulas that they've given on there are the same as the ones that I have. So here under arithmetic, it doesn't tell you that this is explicit, but it is. And here's the explicit for geometric, and it doesn't tell you that this is recursive, but again, you can tell it's recursive because it has that a sub n minus 1. And these formulas are on the formula sheet, the explanation of what the letters represent up here at the top, and you'll be given this on any test or quiz or on your SOL test. Okay, so back here to our packet. A sub n, so the nth term, is equal to a sub 1, where a sub 1 is the first term. And then in here, we're going to plug in the n for whatever one we want. So if we want the fifth term, we plug in n equals 5. And then the last letter in there, d. D is the common difference, and we'll know that from looking at our pattern. So here's an example of an explicit formula for an arithmetic sequence. And you can tell if we plugged into this, if we plugged in n equals 1, we would have a sub 1 is 15 plus 1 minus 1 times negative 5, which equals 15. If we plugged in a 2, a sub 2 would be 15 plus 2 minus 1 times negative 5, because we now plug in a 2 for n instead of a 1, and that would equal 10, which is the second term in our sequence. So you can see it's like a function because you plug in whatever term you want, you plug in that number for n, and then you get out the answer. We like this one because if we have to find the 100th term, we could just plug in 100 for n. Whereas on a recursive formula, if we wanted to find the 100th term, we'd have to go through and find all 99 terms before it in order to find the 100th. Okay, so the explicit formula for a geometric sequence is right here. That's a sub n, so the nth term, is a sub 1, which is the first term, times r, which is the common ratio, and that's going to the n minus 1 power. Be sure you realize the whole common ratio is raised to the n minus 1 power. If I were putting this in my calculator, I probably would write it like this. So just watch out for that. All right, and then here's our example. If we have a sub n equals 5 times 2 to the n minus 1. If we plugged in numbers to that, if I plugged in a 1, I would have 5 times 2 to the 1 minus 1. So that would be 2 to the 0 power. So that would be 5 times 2 to the 0, which is 5. If I plugged in a 2, I'd have 5 times 2 to the 2 minus 1 power. So that's 5 times 2, which is 10, which is our second term. And so on and so on. Every time we're going to multiply by another 2, and you can see that's what happens here. Every time my term doubles the term before it. All right, let's turn over to the next page. It says write a recursive and an explicit formula for each. We'll do number 11 and number 13, and then you guys can try 12 and 14 on your own. So if I were looking at this, first thing I'm going to need to do is figure out, is this arithmetic or is it geometric? Well, every time what happens? I add 4, so 4 is my common difference, and it's an arithmetic sequence. So if I look up my formula, recursive formula for arithmetic is a sub n equals a sub n minus 1 plus d. So I'm going to plug into this formula. Remember, I need to give more information than what's on the formula sheet. I need to start out and say, what's the first term? Well, the first term is 3. That tells me where to get started. Then to get the next term, you're going to take the term before it, and you're always going to add the same amount, and that same amount that you add, you're going to plug in 4 for d, because that's what we got up here as our common difference. I also, if it were the state, they would have put n is greater than or equal to 2. It doesn't matter to me if you do that, but that's what we would put. Okay, if we were going to write an explicit formula for this, I would look up the explicit formula on my formula sheet. That's a sub n equals a sub 1 plus n minus 1 times d. So in the explicit formula, I'm going to need to start out with an a sub n. Then I'm going to plug in a sub 1 for my formula, which was 3. Then I need to leave the n minus 1 in the formula, so I have something to plug in for n. And then I'm going to plug in d. D was 4, my common difference, so I plug that in. I can leave this like this, that's fine with me. Or you could distribute the 4 to both terms, and then you'd have 4n minus 4. And you could write a final version of the formula as a sub n is 4n minus 1 if I combine like terms. Again, it doesn't matter to me which way you write it, but you should recognize if it were a multiple choice that it could be written either way. I'll let you guys try number 12 in class tomorrow, and then we can look it over then. Number 13, to write an explicit and a recursive formula. Again, we're going to figure out what is the pattern. Well, in this time, every time I multiply by 1/5. So this is geometric with a common ratio of 1/5. On our formula sheet, the formula for recursive was a sub n equals a sub n minus 1 times r. If I'm going to write this on my own, I know for any recursive, I have to start out and say, what's the first term? Well, the first term was 15. Now that I've got the first term, I can then base the other terms off of that. So a sub n equals, and then up here we have a sub n minus 1. That's what I'm leaving plugged in as my variable each time. And then I'm going to plug in my common ratio. My common ratio was 1/5. So that goes in here. This is how I would write it. Again, if it were on an SOL, they probably would have n is greater than or equal to 2. They also might have written the 1/5 in front of the a sub n minus 1 right there. That would be fine as well. The explicit formula for a geometric sequence is a sub n equals a sub 1 times r to the n minus 1. So I'm going to plug into my explicit formula. I'm going to plug in everything except for the n, because that's my variable on the right. So first I pick a sub 1, which was my first term. That was 15. I always write my common ratio in parentheses. That was 1/5. That also shows that both the 1 and the 5 are being raised to this exponent of n minus 1. And that's all we need. I'm going to cut this video off here so it doesn't get too long, and then we can do the rest of the examples in class, or I can also post the answers and you can look at them on the PDF. Thanks.